Science fiction and fantasy often blur the lines between fact and fiction, yet black holes are the material of both. Here are some widespread black hole myths that you won't ever believe again. Are black holes monsters devouring everything in their path or doors to other worlds? How much of the content we see in movies is based on science fact and how much is science fiction? According to Dr. Amanda Bauer, an astronomer at the Australian Astronomical Observatory, most people know that a black hole is a very small volume of space with a lot of things in it, so that its gravity is so powerful nothing can escape from it, not even if it's traveling at the speed of light. Black holes, however, are much more complicated than that. When our sun expires, it will turn into a black hole. No, the sun isn't so big that it might turn into a black hole. Instead, the sun will grow to become a red giant star with a diameter that may equal Earth's orbit in around 6 billion years. The sun will then become a white dwarf by exhaling its outer gaseous layer and leaving behind its blazingly hot star core. If the sun were a much more massive star, it would die violently, exploding as a supernova and leaving behind a neutron star, which is an extremely dense object. A stellar-massed black hole is created when the core of a star that is 10 times as massive as the sun supernovae past the neutron star phase. Because you cannot see black holes, they do not exist. Although light cannot escape from black holes, this does not exclude other methods from detecting them. Black holes have an impact on the space around them, which astronomers can observe. While black holes are invisible to the naked eye, they have been mathematically understood since Albert Einstein's time in the early 1900s, according to. We can observe how black holes impact the stars circling them with contemporary telescopes. SGRA, a black hole in the center of the Milky Way galaxy, emits no light, but explained that it is possible to observe individual stars orbiting it on very elliptical, extended routes rather than in beautiful, circular orbits. According to, we can observe a few dozen of these stars orbiting SGRA and apply very elementary physics equations to determine the mass of each one of these stars and the object they are orbiting in order to explain the motion of that star. And you discover that there is something there with a mass over 4 million times that of our sun, but in a very little area with no light at all. Nothing else that we can conceive of that it might be besides a black hole. Like a huge vacuum cleaner, black holes will draw on all the matter in the universe. Thankfully, this is unlikely to be the case. This is due to the fact that gravity is weaker the further away you are from a black hole, and that you must be very close to one in order to experience its strength. If the sun could somehow transform into a black hole, which, as we've already established, it can't, all of its contents would be compressed into a tiny space that could be a few kilometers broad. Consider what would happen to Earth. If the sun were a black hole rather than a star, it would still contain the same mass. In terms of gravity, your mass and distance from Earth are the only factors that matter because they are both still the same and remain 150 million kilometers apart. As a result, gravitationally, nothing alters. Earth just continues on its orbit without being aware that the sun has suddenly transformed into a black hole. On the bigger scale of the galaxy, the same process also occurs. However, on Earth, conditions would be much more gloomy. Remember that SGRA, a supermassive black hole, is at the center of our galaxy, and that our sun simply orbits it along with the rest of the galaxy. Whatever is there causing that mass doesn't matter to the sun. We are separated from the black hole by hundreds of billions of stars, so gravitationally we don't care what it is. To be drawn into the black hole, you must be very close to it. You go through a wormhole to another location and time when you enter a black hole. It is theoretically feasible to do this. However, this alternative has a number of issues, including spaghettification. You might have a wormhole connecting you to another location in the universe, and on the other side, you might emerge from a white hole. However, these are highly sensitive fixes. This solution disintegrates if the black hole undergoes any changes, if something falls into it and disturbs it, or if the black hole starts spinning. Although mathematically plausible, it is not very likely. We probably won't ever be able to find out either. We will never be able to measure this scientifically because we could not get a signal out of a black hole to tell us what was happening. The signal won't be able to escape a black hole's gravitation because it will travel at the speed of light. As an item approached the event horizon, the boundary beyond which light can no longer escape a black hole's gravity, it would also feel enormous quantities of gravitational force. For instance, a clock falling towards a black hole would gradually begin to stretch and be pushed apart because the side closest to the black hole would experience a much stronger gravitational attraction than the part farther away. We've got a word for it. We refer to this process as spaghettification, in which you are reduced to your individual atoms as a result of being drawn into the black hole. The ticking of the clock would appear to slow down as it approached the event horizon if it somehow miraculously managed to survive spaghettification and you were able to observe it ticking. This is due to the fact that time slows down as one approaches a large body, such as a black hole. However, because the time is still passing at the same rate, it appears as though nothing happened. When a big star dies, supermassive black holes are created. Most galaxies have supermassive black holes at their centers, but it is unclear how they develop. One theory is that the very first stars, which were created in the Big Bang 13.8 billion years ago out of nearly pure hydrogen and helium, were larger than the stars we see today, maybe having hundreds of times the mass of the Sun. These enormous, extremely hot stars consumed all of their nuclear fuel within a few million years before blowing supernova and creating the first black holes. These initial black holes, which probably formed in locations where a lot of gas was accumulating and creating the earliest galaxies, sank to the center and developed over time, eventually generating supermassive black holes. Another explanation is that two adjacent black holes combine to generate progressively larger black holes, leading to the formation of supermassive black holes over time. We don't yet know whether this is the creation process, but it's a good theory. The main challenge is that we haven't seen any intermediate-sized black holes or anything between stellar mass and supermassive black holes. Black holes will engulf the universe. You can take a deep breath of relief knowing that this is unlikely to occur. The cosmos will go through numerous transitions in the future, but these changes won't happen for many trillions of years. Black holes are extremely long-lived and will continue to consume material, growing more enormous, but they don't stay forever. Eventually, stars won't be able to form anymore. Hawking radiation, a process that progressively extinguishes black holes, will take trillions of years to complete. The cosmos will eventually burn out, no new stars will emerge, and there will only be a period of time known as the black hole epoch, which will be dominated by these gigantic black holes as they slowly vaporize. In the end, all that's left is a great, massive, vast emptiness, very cold and dark, with thousands of small, elementary particles flying around, but nothing actually to bump against. That was for today. Thank you for staying with us. Don't forget to like our video and subscribe to our channel.